Empezamos.
Sí, si quieres.
So we will start with the last talk today. So the last talk today is Abdon Choque from Universidad Michoacana de San Nicolás de Hidalgo, and he's going to talk about the relation between extremal solutions of the truncated Stieltjes moment problem and stable polynomials.
Thank you, Manuel, and thank you, Carlos, for this opportunity. And I would like to say congratulations, Professor Natig, and it's a very pleasure to know you. So we'll talk about two sets of polynomials. One is the set of Hurwitz polynomials, which are also known as stable polynomials. The other set will be the orthogonal polynomials. But we will take now in attention these extremal solutions, which are extremal for the Stieltjes matrix moment problem. Well, in the title it's not announced matrix, but I prefer to speak in matrix because somehow I work with matrix, then we'll have easily then a scalar case. So, there is definition of given a, let's say for the moment, a scalar polynomial, all the coefficients are real, then such a polynomial is called Hurwitz or stable polynomial if the roots of this polynomial are all in the left-hand side of the complex plane. One theorem in the book of Ganmacher's book, Theory of Matrices, says that a polynomial of degree n is a Hurwitz if and only if such relation holds. Means that this is a continuous fraction expression, and so this number should be all non-negative. This should be non-negative, possible zero, but all others should be positive. So what it means that every polynomial of degree n can be written in this way always, and then just take the h part and g part, divide them, and one can have this relation. So then another theorem in the same book, the volume number 2, says that the real polynomial of degree of even degree or odd degree is Hurwitz polynomial if and only if these quadratic forms are positively definite. In the case when we have the odd degree, it's necessary to look at this number, which Ganmacher calls s minus 1, should be positive, and it's because that when they take this Gn part and here should be the h and Gn and h part, and the Taylor expansion has this s minus 1. So this is very important because actually our approach we don't need this number, and it makes possible to make this connection between this Hurwitz polynomial and orthogonal polynomials. So now here I recall the expansions which Ganmacher uses. This is an even degree and odd degree, and but we use this expansion instead of this 4. We use the number 5 expression for the odd degree of polynomials. So now we will reduce our attention now to we'll pay attention in this Stieltjes matrix moment problem, and it is the following. So if we have a finite sequence of Hermitian Q times Q matrices, they are Hermitian, then it's required to find a set of measures belonging positive measures such that 6 and 7 holds. And this M stands for a possible mass at infinity, could be 0. So the existence of solutions of this problem is the following. So one should look one should construct the Hankel matrices. There are block matrices, 2 of them, and then the results is like the following. If these two, then there exists a solution if these 2 block matrices are non-negative definite. I mean, these relations are completed, and say for n equal to 2n, we have 2 matrices in the same way for the odd case. So, and we will call our approach is mostly in the moment problem approach. I mean, we took the main object, the moments. So we will call the sequence an odd sequence or even sequence. We will call positive Stieltjes sequence if this Hankel matrix will be positive. Both of them. This should be 2 here, and this should be 2 here. So both should be positive definitely. So as usual, to translate the problem of looking of measures to the problem of looking some function, which they are Stieltjes functions. One constructs a Stieltjes transform. So given a measure, one can always construct such a function, and from the inverse Stieltjes formula, one can recover the measure. So this is after normalizing, and we have the action between these 2 sets. So then we can actually look for these functions we are going to do instead of the measures. So, and we call with this symbol the set of all associated transforms to these moments we're looking for. So now the solution of this problem is given with the help of linear fractional transformation. It's usual when here all of them are matrices, Q times Q. This alpha, beta, gamma, and delta are constructed from the given data. It means from the momentum, for the moments. Could be the odd or the even or the odd number of moments. They are different. Here, these 2 blocks are different. They are all polynomials. But in the case when the H1j and H2j are positive definite, when we have an infinite set of solutions which are described with this P and Q. This P and Q, he has written, this problem was first solved by Abdon, and he gave this set of pairs PQ, which should satisfy these 3 conditions. And then to describe the set of solutions, he introduced an equivalence class. He says that if there exists a matrix Q such that Q and Q inverse are meromorphic in this set, then then this P1 and Q2 we'll call equivalent. Then one constructs this equivalent set of classes, and with this equivalent set of classes, one can actually describe this complete set of solutions of this problem. So now some words about the method. Actually, where are the roots? So this approach belongs to what type of method? It consists in reducing this moment problem to inequality problem. So first we define such inequality. Here is written for the Hamburger moment problem. So, and for the Stieltjes we will have 2 inequalities, but here I prefer to write just one. Then one constructs such inequality. This matrix will we can see here. So this H is again one Bloch-Hankel matrix, and here there are some also this is also a matrix constructed from the moments. Here some auxiliary matrix. Then if one is given the moments and one constructs this inequality, and the problem is done to find this function S of Z. And the method consists in transforming this inequality in another this equality here down, marked with FMI2, where it appears here this resolvent matrix, which will play a very important role in our talk. And here also it's constructed explicitly from the help of moments. So given we construct this inequality, and we could transform this inequality in this one, and from that we can give solving this inequality now, this equality here down, we have this solution, the set of solution of this moment problem. So here this omega spatial will run all the class of such functions where mu of t is a function or a function of non-decreasing and all error, or a positive measure in error. So here this is usual in the scalar case, but in the matrix case we could use this such notation. So this works in the base of this theorem. We say that this function S is a solution of this matrix inequality if and only if this S will be the associated solution to the truncated Hamburger moment problem. So in the same way it works for the Stieltjes moment problem, to truncate it, but with two inequalities, and it's a little bit more difficult because there are two inequalities we should somehow arrange to be solved. So one example of this inequality here for three moments here, for instance, this will be this inequality. So given these three moments, the problem here can be to find this function S of Z. So okay, then this is very briefly speaking how the method works. And here is also important this signature matrix is JQ. It's also Pauli matrix, which was already mentioned in some talks before. And this is A matrix is short contractive expansive. These inequalities are the equality holds, and if we write this resolvent matrix in this form, then we can prove that these conditions can be proved, so verified. So it's interesting that we can explicitly find this inverse in this way, and one uses this in this identity. So this is very important facts of the Patap schema we use in the way, and I wanted to recall now. So now we again we return now to the result of Euclid, and when he gave now this the set of solutions of the truncate in both cases and the even and odd case number of moments, and he wrote the set of solutions this way. With the parameter set is here written here in this here from 1 to 3. So again, this theorem says that there is a bijective correspondence between the associated set of solutions S and the equivalent classes of this pair P and Q. This is the Euclid result. In this 1991 was done with the even case, and 2003 was done for the odd case. So now we will need now this we will need this matrices to define orthogonal polynomials. We need, and here this is the auxiliary. Already appeared before. This matrix auxiliary one. Here we construct some matrices which are also dependent only from the moment, from the given moment. And here we construct this definition of some polynomials. Here we construct them. See, all of them were defined here. The elements were defined before. We have two polynomials, P1j and P2j, and these Q are called the second kind polynomials of this this Q1j will be the second kind polynomial of the P1j. So, and the same here for the Q polynomial, this side. And we can give definition of the orthogonality of this matrix polynomials in the following way. So we say that the degree of the matrix polynomial is Q if if the matrix, bigger matrix from the will be with determinant not 0, or in some cases equal to 1, or invertible. Here is written, and the orthogonality is more not non-classical. What we use this orthogonality with the help of this Hn, this is the Bloch-Hankel matrix with the construct of the moments, and here this here the Zn will be this vector constructed with this matrix actually from the coefficient of the polynomial. So, but here I wrote this typical definition of the orthogonality in the matrix case. There are some people who work in this direction, including Simon, and he was Professor Duran, with Lopez Rodriguez, Dete, Grumman, and so other people with these polynomials. And now, so here we use actually this definition of orthogonality. Here is the H hat. It is the same as the norm of the polynomials which appear already today. So in the scalar case, and here actually we call this the sure complement, which is here written explicitly. So now it turns very interesting to give another form of this resolvent matrix we already mentioned, and we last year it appeared in the linear algebra. We gave another form of this resolvent matrix with help of these polynomials which we showed before. This here appears with the second kind polynomial and the first kind polynomial. This is a combination of these four polynomials here, and we gave rewrite the set of solutions with the help of these polynomials here. This PQ small will be the same set as Dukarev. So, so the same here. That's just the written is different, little different, but will be very convenient for our purposes. So, it's interesting the case here when this pair P and Q will be this special one, this the identity matrix here in the first place, and the 0 in the second, and the opposite here in the other. Then we will have these solutions are called extremal solutions, and actually it has connection with the extremal solutions which Simon describes, these Crane and Friedrich solutions. When the operator, symmetric operator extended, then it could happen that there are two extensions. That is the connection. There is connection, but we don't make this connection explicitly. But it can be done. So we call the Crane extremal solution this matrix, and the Friedrich the other matrix. So again, I said we have this from this set of solutions from the spatial PQ. So here is written, and the other we have the odd number of moments. The same here we have two extremal solutions. So actually, this extremal solution it's an interval. So the Friedrich is the interval in the left side, and the Friedrich is in the right side. This is, and between this between this matrix interval, all inside within this interval, all other are also solutions of the problem. So then, to talk about a little more details of these extremal solutions, Dukarev in 2004 he gave this theorem where he described some properties of these extremal solutions. For instance, he succeeded to write these two Friedrich and Crane solutions, this difference, the inverse, in like 32, and the same for the other extremal solutions. And then this is crucial here, number 2 and 3. Here we can see that actually the Crane solution is in the left, and all other solutions are in the middle, and we have one extremal solution on the right. So this is the Friedrich and Crane. So here is some details of the proof, but I think we could now leave. And yes, here he uses actually some interesting connection with this P matrix, which also he uses in his definition of Q, this part PQ, and then he actually proves that this inequality, which actually shows this number 3. Okay. Then it's very important here to mention this Blaschke-Patapov factorization of this resolvent matrix. Yukarev in this work 42, he succeeded to write this resolvent matrix in every case in very simpler way. This simplest way. These matrices L, M, and L are here described. They are constant, low constant matrices constructed from the momentum, and this generalizes this Ganmacher Crane in the 50s, where they wrote this L and M, small m, to solve some mechanical problems. So then we now we return to our form of this resolvent matrix, in this case, for instance, and we wrote now this this expression, which is continuous fraction in the terms of this ML, the same from the other extremal solution. So now this is about extremal solutions, and now now we keep in mind this. Now we are talking about Hurwitz type polynomials. If one here omit matrix, then just there will be the Hurwitz polynomial. So again, this F is a Q times Q matrix. Every coefficient is a matrix, and again we can define the H n part and G n part, and again we can write this polynomial here as 40, and we define such matrix, this matrix 37, as a matrix Hurwitz type polynomial if this J n and H n part can be written in this form. There exists some positive matrices that is possible to write in this form, and the same in the odd case. So this definition. So of course this coincides with the scalar case. Will be real. This this will correspond to the real Hurwitz polynomial. But in matrix we define that. Then we can check a remark, which here we have one one lower expansion of this relation for the even case, and the same for the odd case here written, and we can look at this relation between this. They are the coefficients of this polynomial f from both sides, and here are the moments. And for the 6, they are also again they are the relation between these coefficients and the moments. It's very important to mention that actually this relation appears in the Ganmacher, but this doesn't appear. It maybe was the reason, and also they think that S minus 1 appeared, and that's the reason why they didn't couldn't connect with the orthogonal polynomials. So, but we have written this connection. Then we can now actually write. Say from one side we have h and u for u is equal to this part, to this expression, and in the same time we have this polynomial p1m is the same, so multiplied by -1 to m. So then we have one equality here, and then here's the proof. Then we have done as a remark that it's possible to write this equality for h and j parts of in terms of some member of orthogonal polynomial. So we have that. But the difficult part is the following. So having this extension, this expansion, this continuous fraction, to construct the moments such that the moments could be positive sequence. So this was done here. This is a proposition also in this year, 2015. So given now a sequence of matrices, two sequences, they are positive sequences, then we can we construct some other matrices in such a way, and it happens that this sequence will be even in the odd case will be a positive sequence. It means then we can actually then we will be able to connect with the orthogonal polynomial, and the proof is connected with the fact that these matrices are positive, and we recursively construct such matrices here like 56. And we use this lemma. It says that the matrix A, block matrix A, is positive definite, is equivalent to the fact that this block A11 is positive and the others also positive. This is the sure complement, and the same from the A22. So we use this lemma, and then we are able to prove that this sequence constructed from the coefficients of the continuous fraction are in fact still this positive sequence. Then with this proposition, then here before of the result, I mentioned here one example. If we are given, for instance, this continuous fraction, this one here is the dj is 1 over j plus 1, and c is equal to 1. Then we recover the moments. So, and then we can recover the Laguerre polynomial. So for instance, and then we can write a lemma that let f be a matrix Hurwitz type polynomial, and then there exists a positive sequence such that this expression holds. So we have already somehow explained with the previous remarks how this is done. And other lemma says that let these now list two matrices. This is P1 or Q2M. This is second kind polynomial. And correspondingly, the other part be a member of the orthogonal matrix polynomial and 0 infinity. Then this polynomial is a Hurwitz polynomial. So again, this is based on the fact, the proof of this lemma is based on the fact that when we take these polynomials, and we immediately have with this construction, we remember that we have extremal solution. So now these two theorems are main theorems of the talk. So it says that let now this polynomial P1M Q1M correspondingly the other polynomials, member of this such orthogonal matrix polynomials in 0 infinity. Respectively constructed by positive sequences of moments. So, okay, and then f is a Hurwitz type polynomial if and only if this representation holds. They are matrices, matrix polynomial. So, now for the scalar case, now of course, if one considers this system, ODE system, where this matrix A is n times m matrix, then we know that to check if this system is asymptotically stable in a Lyapunov sense, then one should check this, the zeros of this characteristic polynomial. If all the real part of the zeros are in the left-hand part of the complex, left-hand side of the complex plane, then will be asymptotic stable system. Now then we can apply our theorem, then say that a system, this ODE system is asymptotically stable if and only if the characteristic polynomial of this matrix has this form. So in this way we have a connection between the families of Hurwitz polynomials and the families of orthogonal polynomials. So, well, this part are studied by people who makes control theory, system theory, and this part, orthogonal polynomials, there are people here study a lot of here about this topic. So it's some bridge of these two kind of polynomials or maybe areas. So here, one example. For instance, we can give now Markov parameters or moments. We can give the moments. Here they are j factorial. We construct this Hankel matrices, and we can explicitly give this, construct these polynomials, orthogonal polynomials, and then from them with the given formula we have these Hurwitz polynomials. So this is one way to construct Hurwitz polynomials, and now we know that every Hurwitz polynomials are actually some member of orthogonal polynomials in zero infinity. So this is one fact. And here now in the scalar case, one can now have this remark, and the connection between the moments and the coefficients. So I should say that for m equal to 2m, it was written in the 60s already, but this in the odd case is new because it's a consequence of our results now. Now we have this connection between these moments, and we can write this theorem. Well, not now, but let's recall now that we have a Hurwitz Hurwitz matrix, and we have this Hurwitz matrix. It's well known, this criteria by Hurwitz. It says that having this Hurwitz, this polynomial now with real coefficients, one constructs this matrix, and to answer in the terms of this coefficients, not looking roots now, on the coefficients only looking, if this function has real part, has roots with real part in the left-hand side, then it's necessary and sufficient to check if the determinants, minors of this matrix are positive. So as here. So this is a very nice criterion, and the connection of this criterion given by Hurwitz with our approach is the following here, this theorem, which says that a polynomial with degree odd or even is Hurwitz if and only if these now Hankel matrices we constructed are positive both. So again in the odd case is this new because as we checked in the beginning, here Ganmacher gave this criteria, but he need this number for the s minus 1. So now it's interesting, the question, we're working on that, the relation between these two sets. So we have, in this expansion, we have s tilde, which begins with minus here, minus 1, but we have not minus 1. So, but it happens, it results that we have one very nice relation. It's connected with a solution of another Stieltjes moment problem. So, but this is for another talk. So, yeah, and then, so I think it's, before that I have some references here. So yeah, we mainly use these two words here in linear algebra. Here there are 2 and 15, and also some other here previous works. So thank you.
We'll have some time for questions. Everything is tired. Everybody's tired. So
Okay.
we thank again Abdon for the talk.